Hello everyone, my name is Hedil Zomita and today I'll be presenting Genie, a groundbreaking project developed by Google DeepMind in collaboration with the University of British Columbia. So we'll be having an overview and the challenges addressed by Genie, model components and architecture, model performance and evaluation metrics, limitations, implications, and conclusion. Genie is a major step forward in generative AI. It can take a single image, whether a real-world photo, a sketch, or an AI-generated picture, and turn it into a playable, interactive environment. What makes it truly exceptional is that it learned purely from observing 200,000 hours of gameplay videos on the internet without any manual label or supervision. The problem that Genie tackles is ambitious. Can we build controllable interactive virtual worlds starting from single-point inputs like images without needing manual labels, domain-specific rules, or a full game engine? So Genie's goal is to allow users to interact with these generated words incrementally, frame by frame, as if they were exploring a mini-game based purely on what it learned by watching videos. Genie's contributions are significant. First, it's the first model capable of creating playable environments from a single image input. Second, it learns fully unsupervised, no action, annotations, no domain-specific tuning, just by watching gameplay videos. Third, Genie introduces a scalable architecture combining a video tokenizer, a latent action model, and a dynamic model. Finally, its approach could profoundly impact not only game design, democratizing it, but also robotics by enabling agents to learn in virtual worlds. So here's an overview of how the Genie model training began. It starts by taking T frames of video as input. These frames are tokenized into discrete tokens using a component called the video tokenizer. At the frame time, the latent action model infers latent actions between each frame. The information from both the tokenized frames and the latent actions is then passed to the dynamics model, which generates predictions for the next frames in an iterative manner. To talk about the components, we also need to discuss the architecture behind them, including the spatiotemporal transformer architecture, which takes design cues from vision transformers. The researchers didn't use classical vision transformers because they realized that the computational and memory requirements were too high, reaching up to big O of 10 to the fourth tokens for video processing. To address this, they developed a new architecture that balances small capacity with computational constraints. Here's how it works. We start with input tokens, which are processed through spatiotemporal blocks. Each block contains a feed-forward layer, a temporal attention layer, and a spatial attention layer. Each color in the architecture diagram represents a single self-attention map. The spatial attention layer focuses on different areas within a single time step, treating each part of the grid separately. The temporal attention layer focuses on a specific element across all the time steps, treating the sequence of frames one by one. The latent action model has four interesting aspects. It is in the component that learns from unsupervised unlabeled video frames. It has 300 million parameters in total with a batch size of 16, a very small percentage compared to the overall parameters of the full model. It preserves the spatiotemporal transformer architecture. Additionally, the researchers limited the codebook, meaning the possible latent action output to just 8 unique codes. In the diagram on the far left, we have the input frames. The adjacent block beyond the dotted line represents the next adjacent frame. The encoder processes these frames, generates a latent action, and through the decoder, helps predict the possible next frame based on the defined latent action. The purpose of the video tokenizer is to compress videos into discrete tokens, which helps address dimensionality and video generation challenges. It uses a combination of a video quantized variational autoencoder and the spatiotemporal vision transformer described earlier. The tokenizer generates discrete representations for each frame. In the diagram, we can see video frames passing through the encoder to create tokens, and then decoding those tokens to reconstruct the predicted frame outputs. The dynamics model takes both the tokenized video frames and the latent actions as input to generate predictions for the next frame. It uses 16-bit floating point representation and applies query and key normalization for more stable training. At inference time, it performs 25 masked generative image transformer steps to sample each frame. It processes video tokens and latent action embeddings to predict the future masked video tokens iteratively. This graphic demonstrates how Genie performs action controllable video generation at inference time once the model has been deployed. On the far left, the block above, X1 represents the initial image provided by the player. This image is tokenized using the video encoder producing Z1. The player then specifies a discrete latent action by selecting an integer from the codebook. The dynamics model takes the frame tokens and the corresponding latent action and predicts the next frame tokens resulting in the Z2 block. This process is repeated in an auto-aggressive manner, with tokens being decoded back into video frames, producing X2 and subsequent frames. Now we'll move into some of the model results. In this image, we can see the prompt frame alongside adjacent frames generated after applying latent action multiple times. In the top row, the character jumps off the platform on the top left, starting from a text-generated image. In the second row, the prompt is a hand-drawn sketch. Here's the pink soccer ball moves upward to the right. And in the real-world photo example, at the bottom left, a dog moves to the left of the frame. The researchers were confident that Genie had applications in reinforcement learning. Here's an example of generating trajectories in unseen reinforcement learning environments. So for player 1, we see the character moving to the right and then jumping up. For player 2, the character is scrolling steadily to the right without the upward movement. We can see that the environment remains pretty consistent between the counts of imagery across each slide. This slide is demonstrating that the Genie model scales very well with the addition of more model parameters. We can see that the training loss decreases with an increase in model size overall. Additionally, increasing the batch size leads to better model performance as well. So what they use to evaluate the success of Genie in particular were two model metrics, including threshold video distance. The way we interpret this is that it measures the quality of the video generation, and the lower the value, the better the performance, as well as controllability, which is peak signal-to-noise ratio, measuring the impact of latent actions on video generation. We actually want a higher value here, which indicates greater controllability from the latent actions. In this slide, I included an image from a different domain, specifically in the robotics domain, where each column demonstrates a robotic arm movement from a particular prompt. As we move to the right from each prompt, the resulting frames show the same latent action taken 5 times. And even without training with action labels, the same actions are consistent across different prompt frames. Each column has a semantic meaning: down, up, and left. In the top case, the robotic arm takes an item and places it into the drawer before returning. In the middle example, it attempts to pick up a bag of chips, which is not a rigid object. And in the bottom example, the arm returns an object from the drawer into the table. There were 3 main issues and areas of improvement identified by the researchers. First, Genie still has the potential to hallucinate some unrealistic features. Second, it's limited to 16 frames of memory. And third, it currently operates around 1 frame per second. So while there is still room for improvement in terms of capacity, Genie is definitely on the right track. In terms of implications, we have demonstrated that Genie is very scalable. With additional resources to create larger models with more parameters, it has the potential to assist in the development of even more powerful foundational models. And Genie is also very flexible and can be effectively trained on video-only data, which means it has the potential to work across many more types of internet videos beyond gaming. Its generality suggests the possibility of simulating diverse and realistic and varied environments on a much larger scale. And ultimately, Genie hopes to contribute to the development of foundational world models, particularly in the robotics domain. And that concludes my presentation. Thank you for viewing and your attention.